studying today about enthalpy of neutralization reaction. Okay, enthalpy of neutralization reaction. So first we have to know what is enthalpy of a reaction. Simply change in heat energy. Enthalpy is represented by change in enthalpy, that is represented by delta H. That means change in heat energy, change in energy. A reaction is taking place, how much energy is absorbed, how much energy is emitted. That's what we study. Okay, so here we are studying about enthalpy of neutralization. So in this we will study in a neutralization reaction how much energy is consumed or how much energy is released. So first we have to know about neutralization reaction. What is neutralization reaction? When we react acid with base, it gives us salt and water as product. Water is product. Okay, this reaction is known as your neutralization reaction. Simple. Along with some heat. Along with some heat or energy. Okay, simply if you see this neutralization reaction, if you have considered or carried out an experiment in chemistry lab, this acid base neutralization is normally exothermic in nature. That means it releases energy when we are carrying out this reaction. Okay, so simply we can write acid that combines with base, it gives one salt plus water along with some heat. So for any acid base neutralization reaction, how much heat is absorbed or how much heat is released, to calculate these heat changes or energy changes, we are studying this enthalpy of neutralization. So majorly we will see four type of neutralization reactions. Is if we consider how many types of acid bases are there. If we consider acid, there are two types of acids: strong acids as well as weak acids. Similarly, if we consider base, we have two types of bases: strong bases and weak bases. What are strong bases or strong acids? What are weak acids and weak bases? Simply we can say those acids or bases which dissociates completely or ionizes completely, 100% ionization is there, we call them as strong acids or strong bases. And on the other hand, if those acids or bases do not ionize completely or do not dissociate completely, we call them as weak bases. Okay, some examples are there. Strong acid we may consider like HCl, okay, H2SO4, HNO3. These are like some strong acids. If you consider weak acids, CH3COH, your acetic acid, HCN, these are some examples of weak acids. And if you consider some strong bases, examples are, for strong bases, sodium hydroxide, potassium hydroxide. These are some examples of strong bases. And for weak bases, we have ammonium hydroxide, aluminum hydroxide. These are some examples of weak bases. So we'll study all these four cases of neutralization reaction: when strong acid reacts with strong base, strong acid reacts with weak base, weak acid reacts with strong base, and weak acid reacts with weak base. Okay, so first of all we'll study about case 1, that is neutralization reaction of strong acid and strong base. Okay, if we consider one example, like strong acid, that is HCl, that will be in aqueous medium, plus strong base, that is sodium hydroxide in aqueous medium. If we react them together, they will form sodium chloride NaCl, that will be aqueous, it is a salt, along with water and some heat, and that heat change that is taking place in this reaction is known as delta H, that is represented for enthalpy change, and for neutralization we represent it as delta Hn. That means enthalpy of neutralization. Enthalpy of neutralization. So what happens if we react all these? Like in aqueous medium, it will split as H plus, this will Cl minus, Na plus, plus OH minus, all combine. This will form, this is a strong electrolyte, so it will also split as Na plus, Cl minus, and H2O. Okay, and this heat change will be delta Hn. So if we cancel out all these common ions like Cl minus and Na plus, right side also Cl minus and Na plus, if we cancel out these common ions, my net reaction will be, or my net ionic reaction will be H plus plus OH minus gives rise to H2O. And for these strong acid and 1 mole of strong acid and 1 mole of strong base, that means there is formation of 1 mole of water as liquid, the enthalpy of neutralization is, I may write delta Hn, for which strong acid plus strong base, that is equals to minus 57.3 kilojoule per mole. Okay, minus 57.3 kilojoule per mole. Why it is written as minus? Because when we calculate delta H, we subtract we subtract reactants from the products. As the heat is released, the energy of the products is less, so it is termed as in negative term, or we may write minus 13.7 kilocalorie per mole in calorie terms. Okay, this is for strong acid and strong base. Like if we react 1 mole of strong acid and 1 mole of strong base, that produces only 1 mole of water. In a balanced chemical reaction, the heat energy released will be 57.3 kilojoule per mole. Okay, next if we consider case 2, that is weak acid and strong base. So if we consider one reaction, that weak acid is acetic acid CH3COOH, that is reacted with strong base NaOH, both are in aqueous medium. They will produce sodium acetate CH3COONA, that will be also in aqueous, and H2O liquid plus some heat. Okay, and that is delta Hn किसके लिए? For what? Weak acid plus strong base. Okay, we'll find out what will be the value. Okay, so if we ionize this reaction, this will be splitted as CH3COOH only, as it is an weak electrolyte or it is an weak base. It will not be completely dissociated or completely ionizable. So we cannot write 100% that this will split as CH3COO minus and H plus. So we have to write this only, that will be aqueous. But as our NaOH is strong electrolyte, it will split as Na plus and OH minus. That will produce this salt. Always the salts are strong electrolytes, that are soluble salts. This will be as CH3COO minus plus Na plus H2O. So if we cancel out all these common ions, my net reaction will be this. Okay, but I don't have a value for this reaction. I only have the value that is minus 57.3 kilojoule per mole, that is for this reaction only, that is for this net reaction only. And if we consider this doesn't look like that only. So we have to do something to make this reaction look like that reaction. H plus plus OH minus, that is equals to H2O. Because if we see we can standardize everything, then we have to remember only these two values. We have to remember all these two values. This we have to remember. But we cannot remember these values for each and every reaction. For acetic acid, for ammonium hydroxide, we cannot write down for all these reactions. So we have to make this look like that only. So if I ionize this, give some energy and make it completely ionizable, I provide delta H ionization, or we may write that delta H dissociation. So this will be completely ionized as CH3CO minus plus H plus OH minus gives rise to CH3CO minus H2O, and we may cancel out this, and I have my net equation like this. Okay, and for this reaction I know the delta H value. For this reaction I know the delta H value, that is equals to minus 57.3 kilojoule per mole. But for this reaction the total energy is combination of this and this. So I may write for this reaction delta H neutralization, that will be equals to minus 57.3 kilojoule per mole plus delta H ionization for whom? For my weak part, that is weak acid. Okay. Similarly, if we consider this reaction of strong acid and weak base, for example reaction of HCl with ammonium hydroxide, it will produce NH4Cl plus H2O. And for this reaction similarly we can write enthalpy of neutralization will be minus 57.3 kilojoule per mole plus delta H ionization for whom? Delta H ionization for my weak component, that is weak base. And if I consider the last case, that is weak acid and weak base, such as acetic acid plus ammonium hydroxide, that will give ammonium acetate plus water as product. For this reaction my neutralization enthalpy will be delta H will be equals to minus 57.3 kilojoule per mole plus delta H ionization of weak acid plus delta H ionization of weak base. Okay, so we have to remember only two values. Okay, one in kilojoule scale and one other is kilocalorie scale. Okay, in the kilojoule scale that is minus 57.3 kilojoule per mole. Okay, then we may add the amount of ionization that is required for an weak base, or you have weak acid, whatever it is. Okay, let us consider one example so we can proceed further. Like this, the enthalpy of neutralization of acetic acid is given. Okay, enthalpy of neutralization is 12.7 kilocalorie. Okay, right, with strong base NaOH. So my case is my case here is weak acid plus strong base, and for this my delta Hn, that is equals to minus 57.3 or minus 13.7 kilocalorie per mole, okay, plus delta H ionization for whom? Weak component, that is weak acid, okay. Calculate the enthalpy change for this process. This process is otherwise known as what? Your ionization. This is ionization process, and this heat change will be delta H ionization. So in this reaction, this is given, that is your minus 12.7 kilocalorie. This is a constant, we know this, we have to calculate this. So my delta H ionization for this reaction will be delta H neutralization plus 13.7 kilocalorie, that is delta H neutralization is given as minus 12.7 plus 13.7 kilocalorie, that is equals to plus 1.0 kilocalorie. That is my ionization enthalpy. Option C is correct. Okay. So this is all about enthalpy of neutralization. Okay. So in some questions you will be given neutralization enthalpy, you have to calculate ionization energy, or in some questions you have given ionization enthalpy, you have to calculate the neutralization enthalpy. Okay. That's it for today. Thank you.